Go ahead.
All right, thanks for coming. I really appreciate it, and I hope you will appreciate this also. First of all, a few words about me. As he said, my name is Nicolas Oberli. My nick is Balda. I work as a security engineer at insertH, it's a security company in the French part of Switzerland. I do a lot of CTFs with the team 0 Day Sober. I also love to play old video games on different kind of machines, and I love to drink beer, and I also brew them myself. So, how did I get there? A few years ago, I started building an old arcade machine using a desktop computer and some emulators, so I can play some old video games with friends, etc. And I was thinking about adding the possibility to insert coins to actually add new credits to play the game. So I'm not that greedy, but yeah, getting some money from friends is always fun. So when we talk about coin handling devices, if you try to look at, there are a lot of machines that accept money, bills, or that return the money. If you look all around, there are vending machines for drinks, for cigarettes. If you buy train tickets also, there are in the casino many machines that do this, and there are multiple devices that are used to actually see if you're putting 1 Swiss franc, 2 Swiss francs, or if you try to insert a euro, or maybe false coins. And some of these devices are, for example, coin and bill acceptors. These devices obviously need detect the coin you insert and can send to the device the correct value, and hopefully you will have more credits in the machine to play, to buy cigarettes, etc. It can also detect false coins, and for some of them it can detect multiple kind of money like euros, dollars, Swiss francs, etc. Other devices include coin sorters. They are used to sort coins in different trays. For example, if in the machine there are trays for 1 Swiss francs or 2 Swiss francs, this device, when the coin is dropped, can switch in different trays the money. So it can sort the money in different areas to be maybe it's easier for it to actually get the money back for the vendor. Another kind of machine is what is called a coin hopper. It's kind of a tray that is able to give the money back to the user. So there's a lot of money in the tray, and once commanded to, the hopper can give back 1 coin at a time. This is normally used to give you the money change or something like this. So in those devices, there are many communication protocols that can be used. There are parallel, serial, and 2 other protocols called MDB and CC-talk. Those protocols are normally vendor specific, so each vendor does use a special kind of one of these protocols. And since the coin acceptor I bought for my project was doing CC-talk, that's what we are talking about today. What is CC-talk? CC-talk stands for Coin Controlled Talk. It's a semi-proprietary protocol. Semi in the meaning that if you go to cctalk.org, you can download some of the specs. Some of them are freely available. Some of the other specs are only available after signing an NDA. That's not cool, but could help to really implement all the functionalities of the device we see before. CC-talk works in a way that normally there's a controller, the main board of the vending machine, that sends requests to the devices, and the devices just respond to those requests. There's no TCP-like connections or something. It's just a request and a response, that's all. It works pretty much like a serial line, so it's 9.6 kbit seconds, but it uses TTL signals, so it's between 0 and 5 volts. And one thing that is quite strange. It's only use one physical wire for both sending and receiving. So you only have one wire to send and receive your data. You do it on the same wire. That's quite strange. It uses addresses for all the devices on the bus. By default, address number 1 is the controller, the main board. Number 2 is the default address for a coin acceptor. Number 3 is the default for a coin hopper. And there is a special address that is 0. It's for a broadcast message. So you can send a request that is accepted by all the devices on the bus. All frames use the same format. This is the format of one CC-talk message. There's always 1 byte for the destination address, 1 byte for the data length, 1 byte for the source address, 1 byte for the header. The header is the actual command sent to the device. So whatever header it is, it's the different functions the controller sends to the device to perform different actions. And then you have a variable length of data and a checksum. The payload length, the data length, the second byte of the packet can vary from 0 to 252. So the maximal size of the packet is 256 bytes. The checksum is only the complement to 255 of the whole data. So it's pretty easy to compile the checksum. As I said, there are a lot of headers. Since it's coded in a byte, there are 256 possible commands. And from the documentation, you have a whole list. That's a screenshot of the documentation there, with all the headers and their corresponding function. There are new headers added in new versions of the protocol, and there are headers that are reserved or for internal use only. There may be some things to check with these. To have a look, there's a sample communication. We can see this first request there. It's from the header in green, it's a sample poll, kind of a ping, from device at address 01, the controller, to a device at address 02. It gets a response, header 00, from device at address 2 to device at address 1. There's no data in both of them. And if you look at this, there's a really strange thing. This will cause some problems to actually sniff the data. In the response, you don't have any relation between the response and the request. The response is always 0. So you have to know the request to know to the response what is the corresponding response. Since normally there's only one controller, so it will send the request, receive the response, then send another request, maybe on another device, and get the response. But if you are just connecting to the bus, you have no way to know which was the request for this response. This might be a problem for the future. Another packet sent. The header is F6, request manufacturer ID, again from the controller to the device. And the device responds with a length of 3, and the response is NRI. It's the manufacturer of this coin acceptor. The payload is ASCII encoded. There are other responses that are binary encoded. It really depends on the device or the specs. So, for my initial project, I was able to ping the device. I was able to get some information for it, but now I need to know exactly how to get if somebody puts 1 Swiss francs or another coin in the device. To do this, there's a header number 229 that is sent to the device, and the device sends back 11 bytes of data. That is 1 byte for a counter and 5 results that are of 2 bytes length. This counter is incremented by each event that is made on the coin acceptor. So each time you put a coin in it, even if it's a wrong coin, a false coin, a good coin, or if there's a problem, there will be a new event generated and the counter will be incremented. The last 5 results are encoded in 2 bytes. Normally, in the first byte, there's the validation channel. This is not the value of the coin inserted, it's the validation channel. If you like, it's the ID of the recognitionized piece coin. Normally, a coin acceptor device can recognize up to 16 different kind of coins, and each of them is assigned a validation channel, so from 1 to 16. Normally, they are set by the manufacturer by default, but you can also reconfigure it to, for example, if you have one in euro format, you can change and make the coin acceptor recognize Swiss coins or something. The second byte contains normally the error code. So if it's a bad coin, if the coin was correctly accepted, if there's a mechanical error, etc. And it can also contain the channel where the coin has been placed to. Using this coin sorter, the coin sorter, again, place the coin in different trays, and you will get this information using the result B. The problem is that sometimes result B are switched. So for some vendors of coin acceptors, the first byte contains the error code, and the second one contains the actual value, the actual channel. So you have to look at the datasheet to be sure on how your coin acceptor works. So I have all information to create my initial project. So I implemented the CC-talk protocol on a TIN-C device. For those who don't know who this is, it's kind of like an Arduino. Just look at your badge. But the advantage of the TIN-C is that it can emulate USB devices like a mouse, a serial port, or, what is interesting for me, a keyboard. So what I did is simply implement the CC-talk protocol to poll a coin acceptor device, and since it shows 1 Swiss francs has been inserted, it will send a keystroke to my main cab and add a new credit. To have a look, the TIN-C is right there. A big mess of wires, mostly for debugging purposes. There's a game running behind, and the coin acceptor. If I put 1 Swiss francs, I will have 1 credit. If I put 2 Swiss francs, 2 more credits. If I do it again, it counts to 5. So great. Now I was able to get some money, more, but since I'm a hacker, telling me, but can we do more things? Can we get more information? Or there might be more things to do with this protocol. So I had a look and found several different devices or vending machines that use CC-talk, and I was trying to maybe interpret the data, or at least know exactly how this works in real life situations, not that kind of hack that I did. The problem is that there's no open source CC-talk sniffer for the moment. So I created 2 tools that are called CC-sniff and CC-parse. They are coded in Python, and CC-sniff is obviously used to sniff data on a bus and save data on a file, and CC-parse is a tool to actually parse the data to a readable format, so you can track the requests and responses and see exactly how it works. I had to create a CC-talk library because, again, there are no open source tools to do that. And the best use case you could do is to use a bus pirate to sniff the data on the bus. Why a bus pirate? Because you have on your laptop maybe a serial line. The problem is that they are not in the same voltage as the CC-talk bus. So this is a bus pirate. It's an open source hardware hacking tool. It's really easy to interface this with all kind of protocols, UART, SPI, I2C, OneWire, etc., etc. You can use it using a terminal, or you can also script it for tools like the one I did. So for a quick demo, CC_sniff takes for arguments the serial device, and we select an output file in temp, and we see there the data that is traveling on the bus. If with this data we are using CC parse, there's a nice console interface where you see all the packets, you can select them, and if you press enter, we'll get all the information of the packet, what is the correct name of the header, not only the number. If it's a response, you can decode it, and you can that way track what is happening directly on the bus. We see there the response of a header 229, the one used to get information for a coin acceptor, sorry. And you have the decoded payload with the event counter and all the 5 results in the 2 bytes, and also a next dump of the packet. So with these tools, it's really easy to sniff a CC_talk bus and understand and learn on how does it work exactly. I'm still a hacker, and I said to me, can you do maybe even more? Because we are on the bus, we can listen to the traffic, but are we able to inject data or write data on this bus? Like for example, telling, okay, I'm the coin acceptor and I received two more francs. 2 more francs again, 2 more, 2 more, 2 more, to get more credits for buying cigarettes or something. The problem is that, again, there's only one physical wire for the bus. So if we can sniff the request, we will also, the corresponding device will also do. And normally the corresponding device will respond to the controller before or at the same time as us. And this will jam the signal and raise an error, fire up an alarm or something. So how can we make it to disable the correct device, the target device, to respond at its place? What? Okay. So I looked again at the documentation, and I found some commands called multi-drop commands that are used by a controller to resolve conflicts. For example, if you have many coin acceptors for different kind of money, by default they will all have the address number 2. So the controller can send a command to one of the devices to tell him to change its address to a new one. Either the controller can specify one address, or he can use another header, the header 250, that is address random. So when using address random, the device will try to sniff the bus and use a new address that is not in use at the moment. So with these requests, we may be able to change a device address and start acting like we actually are the device. To do this, just send an address change request and change the target to another address somewhere on the bus. And since it won't respond again to the request, we are now able to respond at its place. So we are directly hijacking the device. We can maybe forward the request to the device or respond instead of the hijacked device. Again, the problem is that there's only one wire, so we have to be sure that we won't jam the traffic. I could be able to do some tests on real vending machines, and I even found one that when there was a jam or there was some kind of interruption, it was starting screaming with an alarm. It was crazy. So I did some calculus, and to send the address change request, it takes about 6 milliseconds. And as the specs said, you need to poll every device every 200 milliseconds. So normally there's largely enough time for us. But the problem is that the more device you have on the bus, the shorter the silence window will be available. Because you have to poll every device every 200 milliseconds. But if you have 5 devices, you have to poll them every 200 milliseconds, but one at a time. So it's 200 milliseconds of silence divided by 5. So the more device, the shorter the window. To sum it up, if you want to hijack a device on the bus, you have to scan the bus to actually look if there's enough silence to inject data. If there's sufficient periods of silence, you can prepare the injection. So look at the device you want to hijack, prepare an address that is not in use at the moment, then wait for a silence period, inject the packet so the device will change its address, and then at this moment we can start responding instead of the target device. After we finished, to be clean, we need to take the device and tell him to get its original address, so we'll stay stealth and normally there won't be any alarm firing up or something. Again, we need to do this while the bus is in use, so we cannot just send all the packets and start responding. We have to check if there are not other devices that maybe are jamming the traffic or are responding ahead of us. So to simplify this, I created a tool called insertH that automates the hijacking process. And it works by sniffing the bus, looking for data, and finding silence windows, preparing the injection, change the device address, and start responding as the device we want to hijack. Again, we are using a bus pirate to sniff, and since it can also inject traffic, that's the perfect tool to interact with the bus physically. As an example, that's the title of this talk, we're able to inject some kinds. Like if you hijack a coin acceptor, you are able to respond to every request, like the one we saw previously, and just respond by incrementing the event counter. Every time you increment the event counter, the last event will be replayed, and if you just put 1 Swiss franc, for example, if you increment the counter, the machine will actually think there's 1 new franc inserted, etc., etc., etc. If you want to do this, you have to be really careful not to set an event counter lower than the previous value, because in that case, the main board will start again an alarm. There are some protections that are made by the vendors to protect hijacking, but normally, if you do this correctly, like sniffing the bus to see what are the last response from the device, and right after hijacking, send the same response before starting modifying them, normally you won't get any problem. To see how it works, again, I have MAME there, so I'm still using my project for this. And with insertH, I use the same parameters as ccsniff. The only difference is that we need to specify a source address, so the actual target address, and a destination address, where we are going to send the device on the bus. So we specified the coin acceptor at device 2 and send him to address 7. And when it's done, we see there the response that has been sniffed by insertH. And if we modify it, it would add 2 more credits. If we do it again by incrementing by 1 the event counter, we'll again add new credits. And now, if I tell him to increment automatically in the machine, we'll start getting more and more and more and more and more credit. Okay, that's great, but maybe we can do even more with this. Like, as, for example, an acceptor is offline, is not responding to anything, so we can do pretty much whatever we want with it. For example, some coin acceptor are able to be reprogrammed by cc_talk, so we can send a header to tell him, just switch in learn mode, and you can say, okay, reprogram the channel number 5, for example. So the coin acceptor will ask for some coins, new coins, and it will start learning about the diameter, the weight, etc. to learn for a new coin. For example, let's say since the main board actually only knows the channel ID of a coin, it has to have a corresponding table between the channel ID and the actual value of the money. So this table is in the coin acceptor and in the main board. So, for example, if 5 Swiss francs, the big coin, 5 Swiss francs is in the channel ID number 5, if you reprogram the channel ID number 5 with 10 cents coins and move back the device to its original address, when putting 10 cents, the coin acceptor will send, there's a new coin with channel ID number 5, and the main board will check, okay, channel ID number 5, it's 5 francs, great. So let's have 5 francs in the credit. But you only have put 10 cents. That's pretty easy to do. On other devices, you also can change the path the coin takes after being accepted. Like we saw, we have a coin sorters that can place money in different trays, and there's always one tray for bad credit or bad money that is sent back to the user. So why can't we change the sorter path from normally getting in the tray, but getting back to the user? So we just put 5 francs, it gets back, and it gets counted. So since you win, just play again. No problem. That's cool. On another topic, for the hoppers, they normally use a special schema to release the money. It's kind of protected. You have to ask for a challenge. It will send you back 8 random bytes. Then the controller needs to encode this challenge with the number of coins to actually send back and send this value to the hopper. And if the challenge and the response match, it will start giving out the money. The problem is that to simplify these steps, because the algorithm is only available when signing an NDA. So I think even some vendors do not have to sign the NDA. And to be more simple, they are not using this kind of challenge response thing, but only use the serial number. So instead of the response encoded with the challenge, you only have to send as the response the serial number of the device. And by looking at the documentation of some hoppers, I also find this phrase: if the hopper product code is blah blah blah, then the dispense card command still needs an 8-byte code, but the value of the code does not matter. So yeah, just send whatever you want, dead beef 8 times, and that's it, you have the money. So if the hopper does not use any kind of challenge response, or you can put whatever you want, just tell him to dispense 255 coins. You will clear it, but you have to do this challenge response thing even if the response is not correct. There's another way, much better. There's a command called purge hopper, and you just send it, and the hopper will start clearing itself, dropping all the money. Why use encryption or challenge response if you have this command? I don't know. Okay, so we found many things to do, but isn't there any protection? Yeah, in the specs there are protection, like a pin code, a 4-digit pin code, that needs to be sent by the controller to the device before actually sending commands. It's only for a subset of commands, and it depends on the device. For example, for a coin acceptor, you are only able to probe for new events after sending the pin code. The problem is that the pin code is sent in clear text on the CC talk bus. So if you sniff, you will get the pin, and you can just send this pin to get the information you want. The actual command for the pin code is header 218. So just look for it. Normally, you only have to do it once, and the device will be in unlocked mode and respond to every command from the controller. But if you really want the pin code, just pull out the power cord of the vending machine, pull it back, and since it will be a reset, you will be able to get this pin code. Since it's in clear text, there's no problem for that. In later versions of the specs, there's also encryption. There are at the moment two encryption methods: a proprietary encryption with obviously no details, you have to sign this NDA, with a 24-bit key, and DES encryption using a 56-bit key. And there's also, for a new version that should be coming in 2013, a version with AES. All of these use a pre-shared key between the controller and the devices, and the encryption uses different headers. For example, we normally use the header 229 to request data from a CON acceptor, and the controller now must use header 112 to read encrypted events. That is encrypted with this key. The problem is that if you really want to know this value, you just have to send the header with the header 229. Even if it's encryption enabled, you are able to send this command and get the data unencrypted. There's no disabling. The clear text header is not disabled when using encryption. So if you really want this information, you are still able to have it. It's great. So we have more things to discover for this protocol. For example, the encryption support. There are maybe more things to do. For example, the keys can be transferred using CC-talk. So the DES key or the proprietary key is normally transferred using CC-talk at the initialization of the device. And since it's a proprietary and closed source encryption, it could be weak. It should be weak because, yeah, in such a small device, you won't have any crypto device or something like this. So normally the proprietary encryption could be easily breakable. There's also a possibility to dump the internal memory of all the devices on a CC-talk bus. Just send a command and it will send you back all the memory pages it has. So maybe you can get information, find vulnerabilities in the firmware, or get private data. It is also possible to upload a new firmware to the device while it's in use. So why not preparing a new firmware with new money configuration and just upload it to the device, and that will be great. For the hoppers, since not all the devices, there are actually some good devices that actually use the challenge response protocol. There are maybe also two things to do with this. I'm still working on this, so there may be a new version or a new tool to crack the key or to break the challenge response algorithm. I'm still reversing an application. Maybe I will speak about this later. And that's pretty much it for this. A few words about the connectivity. Normally these vending machines are locked. You are not able to directly connect to this bus. For the machines I've checked, normally there are two keys. There are one key for the technician that is able to open the machine, fill it up of cigarettes, for example, or to replace a broken device, and another key for the actual owner of the vending machine that needs a second key to actually get the money. The problem is that access to the CC-talk bus normally only requires the machine to be open, because all the CON acceptor devices are normally right in the door. So you have all the cables, you can just connect to it using this. So nearly everyone can do this. For example, an evil employee, or if you see a machine open, wide open, just connect to it and start hacking. At the moment, we need to have our laptop, a bus pirate, connect to this bus, etc. So yeah, you will normally be easily spotted in a casino if you are with your laptop on an open machine to actually try to hack some stuff. That may be difficult. The thing is, and that's another project, it would be possible to use an Arduino, for example. That may be a cool thing to do there. And use a Bluetooth shield, so a Bluetooth interface for the Arduino, and do exactly the same. Inject traffic, inject money, etc., using Bluetooth. So if you're able to find a machine, an open machine, just connect it, close the machine, walk away, come back later, and with your phone, just inject the traffic and add money, for example. That would be possible. In conclusion, specific protocols are really fun to analyze. There are several funny things I found. I didn't know there was those kind of protocols like CC-Talk. I didn't even know about this before buying actually one coin acceptor. There's still more work to do with this. Again, since it's money related, there's always interest for this for hackers. So if you don't have it, also buy a bus pirate and start hacking CC-Talk. Just a word about the tools. All of them will be available just after HashDays. Check out my GitHub account. I will push the application, let's say, on Monday. And that's it. Thank you very much.